Hi, everybody. Welcome to the UW Robotics Colloquium. It's my really great pleasure to introduce today's speaker, Luca Carlone. Luca is from MIT Aeroastro department, and he's done some really exciting work in the broad context of perception and representation. I really like the mapping aspect of his work, where we are always wondering how should a robot represent the environment it's operating in, right? The robotics community has been working for decades on this problem, and it's mostly focused actually on the so-called SLAM problem, where the robot needs to kind of estimate a consistent representation of the environment. And the focus was just about it has to be spatially consistent. For example, I need to take my laser scans and lay them out in a 2D, for example, map of the environment so that everything kind of fits well together. But there are many other aspects that are really important if you want your robot to reason about the environments, right? So we humans also reason about environments very much at a semantic level, right? Talking about rooms, reasoning about hallways and things like that at a much broader, coarser graph style kind of representation maybe. And then if you want a robot that, for example, also does manipulation tasks in the environment, then suddenly there are areas for which you need a really high resolution representation, and that representation needs to be three-dimensional so that the robot can figure out like how it could pick up an object. And the big question is really like, how can we combine these different levels of representations? And Luca is one of the, I think, very, very few people who are really thinking deeply about this problem and actually building a system that brings all these different aspects together. And in another line of work, he's done some really cool research on certifiable algorithms. Now that we get robots that we actually put into the real world and where they really do things, the question is how can we make sure that the things they do actually make sense and that we understand what they do. So for example, especially of course in autonomous driving right now, right? You want to make sure that the analysis that the system does, for example, on laser scans and things like that, that it obeys certain properties that you want to have in there. And Luca, I'm sure we'll talk a little bit about that today. And I'm really excited to see all the progress coming out of his lab. So we're in for a treat. Welcome, Luca.
Thank you so much. By the way, did a much better job at giving an overview of the work than what I'm going to do. So it's a pleasure to be here. At a great morning of meetings, discussion, having a lot of fun. I'm excited about sharing our work with you. I'm happy to get feedback. I look forward also to the meetings afterwards. So the plan for today is to tell you a little bit of the work of my group. I'm going to touch on three main topics, which are hierarchical representations, certifiable algorithm, and self-supervised learning. And with this slide, I'm just going to start with the important things. I'm going to start by giving credits to the many students, postdocs, and collaborators who are making this research possible. Okay? So in my group, we are working essentially on 3D perception and vision-based navigation. I want to spend maybe a slide telling you about what are the applications that are motivating our work. In a nutshell, the applications we care about are applications which are safety critical, high integrity, and highly interactive. And in this slide, I'm giving you just a little bit of the flavor of the different applications, borrowing from the projects we've been working on. So the top left one, this one, and the middle one are examples of safety critical applications. Search and rescue, you can imagine that if the robot is failing to do vision-based navigation, can fail to find survivors. So it's definitely safety critical. The same on a self-driving car. If you're failing to do vision-based navigation, you can put human life at risk because of crashes and so on. And on these two applications, we've been particularly lucky to get really first-hand experience working both on search and rescue and autonomous vehicles. Search and rescue were lucky to participate in the DARPA Subterranean Challenge in collaboration with JPL and Caltech. It was a really fun challenge about deploying robots in tough underground environments and have them map the environment. For autonomous driving, we've been lucky to work with both Ford and NVIDIA on problems such as vision-based navigation, VIO, or fall detection for perception systems. The one at the top right is not a safety critical application, it's a high integrity application. So in this case, we're talking about navigation with a rocket or with a balloon. There is no person on board in this case, but these are very expensive pieces of equipment, so you don't want to break them. And my students have been quite lucky in flying their algorithms on both the platform that you're seeing over there. There is the Blue Origin New Shepard rocket on the right, and there is a high-altitude balloon, which you see over there. And this is the part of the talk in which I have to clarify that the balloon is not the one that you saw in the news a few weeks ago. So the experiments actually worked pretty well. The bottom part of the slide are just an example of highly interactive applications. We care about all sorts of interactions, interaction between multiple robots, interaction with the environment. Actually, we had a lot of fun working on aerial manipulation with a drone picking up objects on the fly, as well as interaction between the robot and humans. Okay, so by working on all these projects, essentially we realized that on the perception side, on the mapping side, there's still a bunch of problems to solve. And we started thinking about three main directions or three main dimensions of the problem for which we need a little bit of an improvement or we need research. I'm laying out the three dimensions in this plot. Some of them are quite easy to understand. The first dimension is robustness. We look for algorithms for perception to be more robust to noise, outliers, and to work far from the training domain. The second is scalability, when algorithms which are scaling to very large systems, to very large scenes, and they're not bound to supervision on a specific scene. The one that is maybe less intuitive is the vertical axis, which is about autonomy and scene understanding. So you can think that by moving down from bottom up along this line, we have systems which are more and more autonomous and have much better understanding of the world. For example, if you have a system with low level of autonomy, maybe the robot is able to execute geometric instructions. Robot go to position X, Y, and Z. But personally, for the future of robotics, I would like to execute my robots to execute much higher level instructions, such as robot, go grab me the cup of coffee on the desk. Okay? So you can imagine that to execute these instructions, the robot will need higher level of autonomy and higher level of understanding of the scene. So let me populate this space with a couple of examples just to make sure you're on the same page. You can think about SLAM being somehow over there. So SLAM is simultaneous localization and mapping. Considering the presence of Dieter, I will not need to tell you much about that. You can think about SLAM as being a very mature technology at this point. It's very robust. It's very, very scalable. The map I'm showing over there is actually a map that we built with a multi-robot system covering tens of kilometers in terms of trajectory length. At the same time, SLAM is not providing much understanding of the scene, right? It's just geometric understanding. So SLAM will be able to support these kind of instructions, but will not be able to support the high-level autonomy capabilities. Luckily, there was the deep learning revolution. We have much better tools right now. So we can pick tools such as 2D semantic segmentation, let's say based on supervised learning. And in this case, we get a boost in the quality of our semantic understanding, our understanding of the environment. I don't know if you can dim the lights a little bit just to make the slides more visible, if that's a good idea. But here, what you see roughly is a semantic segmentation of the image in which you have different colors corresponding to the different classes, semantic classes in the image. The price you pay by doing that is that you get a much better level of scene understanding, but at the same time, the robustness is going down because now you're mostly performing well close to the training domain. And also the scalability is going down because you're reasoning mostly in the image space, so over a much smaller domain. And you can think about this getting worse if you're trying to do some 3D deep learning. For example, for object pose estimation, it's getting worse just because now you need to label things in 3D, and labeling things in 3D is typically harder. So not surprisingly, where we want to be as a lab is over there. Our goal is to have algorithms which are scalable, robust, self-supervised, and then enable real-time scene understanding. Okay? So we want to have the best of all these axes for real-time scene understanding. What I'm going to do in the rest of this talk is really tell you about three different efforts, which are about pushing in these three directions. Okay? And I'm going to start each part of the talk with a slide like this. So if you don't want to pay attention to the entire talk, maybe just look at these slides. I have three of them, which are summarizing the main point that I want to make. So the first point I want to make is that highly interactive and scalable robot perception requires metric semantic, hierarchical map representations, and of course algorithms, systems and algorithms to build them in real time. Okay? So we need metric semantic maps which are hierarchical in nature. I don't think it's too difficult to convince you that we need metric semantic maps. If I want to tell my robot, go grab me the cup of coffee on the desk, the robot will need to know a little bit about geometry, will need to know how to avoid obstacles and move around obstacles, but we'll also need to know the semantics of what is a desk, what is the cup of coffee, and maybe we'll need to reason over relations, like what does it mean for the cup of coffee to be on the desk? So we'll need to have some semantic information. So for this reason, a number of years ago, we started working on Chimera, which is a library for metric semantic simultaneous localization and mapping. What Chimera does in terms of input-output is quite easy. You get camera images as input, these kind of images. You essentially do a semantic segmentation in 2D of the images. And Chimera inside will map this 2D understanding into a 3D model. So the output that you get out of Chimera is a 3D map. You can think about this as a 3D mesh, where each phase of the mesh is color-coded by a semantic label. Okay? So for example, gray is the ground, green are the chairs, yellow are the cubicles, and so on. So all this is done in real time, Chimera is open source. I would say that at this point, this was back a few years ago. At this point, many labs and many companies will have this kind of technologies. I think a few things that still stand out in Chimera are the ones that I'm listing over there. We're able to do this post-graph and mesh optimization, which is a technique to deform globally the mesh to enforce loop closures when you do SLAM. And also we have a lot of robustness to incorrect loop closures because we have fancy algorithms for outlier rejection, which I'm going to cover actually in the second part of the presentation. Something that more on the practical side stands out is that all of this is working in real time on CPU, so you can deploy these on a very cheap, small computer. So hopefully, metric semantic, the need for metric semantic representation will be obvious. What I want to spend a slide on is why we need not only metric semantic, but also hierarchical representations. To do that, I will do this experiment. We're going to think about mapping a 3D environment, a 3D apartment in this case. And I'm going to compare traditional flat representations for the map against newer hierarchical representations. So let me start with flat metric semantic representation. You can think about these as voxel-based representations, right? So I'm modeling the map as a set of voxels, 3D cubes. But at the same time, this is a metric semantic map. So I want to attach to each voxel semantic labels. For example, I want to say that a voxel is an obstacle, has a semantic label being bed, belongs to a bedroom, belongs to an apartment. I want to really store a number of semantic labels to that voxel. And of course, I will need to do the same exercise for all the voxels that I have in my map. Now, with back-of-the-envelope calculation, you can easily realize that the storage, the memory that you need to store this representation, is something that goes with the product of number of labels, L, multiplied the number of voxels. So V is the volume, delta is the voxel size. So essentially, the size of this representation will be number of labels by number of voxels. Now, this is OK if you're mapping an apartment building. That's OK. Maybe the L with neural networks is going to be maybe a few hundred, maybe 100. Number of voxels is going to be in the thousands, but it's still OK. But here we're really thinking about the future of robot perception, right? So we want to have robots in the future which are much smarter. They have much larger vocabularies. So in the English vocabulary, the number of terms, the number of words that you have here is around 500,000. Okay? So now you have to start thinking about the L being 500,000. And we're thinking about very large scale mapping, right? So the number of voxels can explode. For example, if you have an area of 10 kilometers by 10 kilometers, and you want to map these with voxel size of 10 centimeters, you will already get 1 billion, billions of voxels. So now we're starting having billions, which are multiplying 500,000. And this, you can clearly see that this is not going to scale very well. Now, the basic observation that we have is that concepts naturally emit a hierarchical organization. Instead of storing that the voxel is belonging to the bed, to the bedroom, to the apartment, we can just arrange things hierarchically, and we can just say that the voxel will correspond to certain objects. Then we can group the objects into rooms, the rooms into apartment, and the apartment into buildings, and we can keep going as much as we can. In this, for humans, is such an obvious exercise that I don't think I have to spend too much time. But if you do the math, you start seeing that this is already compressing and saving a lot of memory in the representation. You can do even better. You can say, instead of storing a voxel-based map, maybe you can store more of a topological map of the environment, a sparse map of the environment, and you can really bring down the memory, the storage of this representation by a lot. So in summary, the first point I'm making in this slide is that hierarchical representations scale better to very large scale environments and to very large label spaces. Moreover, if you're starting to think at a map representation as a graph, you can easily reason over relations between different things. For example, here the edges are already representing inclusion relations. For example, the stove is in the kitchen is in the apartment. But you can really think about any type of relation, right? You can think about the stove being near the fridge or the kitchen being near the dining room, okay? Or anything, any relation that you care about. So in other words, hierarchical graph-based representations can better capture relations. The last one is an interesting point, it's more technical, but essentially what we do is we prove that hierarchical representations lead to graphs which have small tree width. Tree width is a graph theoretic parameter which is quantifying the complexity of a graph. So if you prove that the graph has small tree width, it means that performing inference or performing many of the algorithms we care about on this graph will be efficient. So for example, if you want to do the graph and you want to do some probabilistic inference over the graph, the proof that the graph has small tree width will allow to do polynomial time or efficient inference. Now you could say, well, we are in 2023. Maybe we don't care about doing inference over probabilistic graphical models. We have a deep network to do that very efficiently. What I'm going to show in a few slides is actually that even if you consider modern architectures for graph neural networks, the tree width of the graph will decide how expressive is the architecture. So what I'm saying here is that the tree width result is a fundamental limit. You can pretend that you have deep learning tools, so you don't care about that, but somewhere you will still hit the same fundamental limits. So this is a little bit of the motivation that pushed us to investigate hierarchical representations, and in particular investigated hierarchical representations called 3D scene graphs, which in this case are focused on indoor environments, and are modeling the environment as a hierarchical graph, where at the lowest layer, you have a 3D map, like a 3D mesh, essentially. But as you go up in the hierarchy, you're abstracting the low-level geometry into high-level concepts. For example, you're abstracting the mesh into objects and agents. It's not super visible, but you see a constellation of objects and humans walking around here. You're abstracting the objects and agents into rooms, buildings. Places and structure, essentially structures are the walls, ceiling, and so on. Places are just locations that the robot can move to. So you can think about this as a graph of locations that the robot can traverse. Okay? And the edges in this graph will be just segments that the robot can traverse. So this is this very messy graph of 3D locations that the robot can traverse. So more formally, a 3D scene graph is a graph where the nodes are spatial concepts, so anything that lives in 3D can be a node, and edges represent relations within different concepts. For example, an edge can say that a human is in a given room, or maybe that an object, here they're not really visible, but an object can be grounded in some portion of the mesh. So why we believe that these representations are powerful? First of all, I already argued that these are scalable representations that they enable efficient inference. They can capture relations among things. But also, if you're coming from a mapping background in robotics, you actually realize that these representations are unifying a lot of the map representations we used in robotics for the last 20 years. There is a dense metric map, which is the lowest layer. There is a landmark-based map, which is this map of objects. And there is a topological map, which is the graph of places that the robot can move to. So it's a unifying representation. Moreover, I'm calling this an actionable representation because now that the robot knows about objects, rooms, and so on, the robot can start executing commands such as, robot, go to the kitchen and pick up this cup of coffee. Okay? We'll have all the information in the map. So of course, we didn't just spend time defining the representation. We really tried to figure out how to build this in real time. And we have a number of works, like what I'm going to present is the most recent effort in building these representations in real time. This is partially something that we presented last year at RSS. The overall system is called Hydra, and it comprises three main parts. So the first part is about building the scene graph incrementally as the robot is exploring the environment. So imagine that the robot is starting in a 3D environment, completely unknown. And as the robot is moving around, is building gradually this 3D mesh of the environment, is estimating its own trajectory, which will show up in a second, is estimating objects around the trajectory, is clustering the free space in this graph of places, and then is clustering the places into different rooms and different buildings. Okay, all these happens in real time on the robot. So at this level, I think most of it is standard geometric processing. We're not claiming a lot of novelty in many of these steps. There are a couple of things which are interesting still. The construction of the graph of places, we figure out a way in which you can do that construction for free as we build them up, so we do not have to do extra processing. And the clustering of the places into rooms is something based on graph theoretical algorithms, which is pretty interesting, but I will not go into the details of that. So this is what we call an odometric scene graph. The robot is exploring around and is building this scene graph as it goes. However, by definition, odometry will drift over time. If the robot is building this scene graph based on his motion estimate, the motion estimate will accumulate more and more error as the robot is exploring around. So let me explain here what you're looking at. So this is a real experiment. You see the images at the top left, except the ones that are removed for privacy reasons. This is a semantic segmentation in 2D, and this is the result of the 3D scene graph construction, both a 3D view and a top view. Okay? So what happens here is that the robot is starting on the first floor of a building, is going up the stairs, and then is traversing the second floor of the building. You see that these floors are kind of misaligned, unfortunately, because there is some odometry drift. At the same time as it happens in traditional SLAM, if the robot is going down the stairs and then is walking back to the original location, you can start detecting and enforcing loop closures. So our contribution here is to show that you can extend the traditional math that you do in SLAM to perform loop closures at the level of the scene graph. So instead of optimizing just the trajectory of the robot, you can optimize, in a single optimization shot, you can optimize all the layers of the scene graph. Not only we do that, but we also show that using 3D scene graphs allows creating hierarchical descriptors for place recognition. Traditional place recognition is based on image appearance. So you look at the image, you extract features, and you see if two images are looking similar. If you have a hierarchy of concepts, if a location, for each location, the set of objects around that location, the room it belongs to. So essentially, you can use all the layers, the information across multiple layers, to design better descriptors for place recognition. This is an example of Hydra, which is this system for 3D scene graph construction running on a robot. I think this is running on the A1 quadruped. Again, video from the onboard camera, semantic segmentation, actual robot, and 3D scene graph being built. More than showing you the entire video here, what I care about is the table, which is at the bottom right, which is summarizing the runtime of the construction of the different layers of the scene graph. All this is running on CPU, is running on Xavier NX, which is quite of a small credit card-sized computer, and you can see the different layers can be built in a matter of milliseconds. Okay, and overall, the scene graph will look reasonable at the end. Okay, so far, hopefully, I convinced you that we have real-time algorithms that are able to build a hierarchical map of an indoor environment, which will look something like this. Again, there is the mesh, objects, humans moving around, and then we cluster these in terms of rooms and so on. But if you look closely at this video, you realize that there is something missing. We definitely have semantic labels for the objects because we use a semantic network to detect objects. But the top part of this scene graph, and in particular the rooms and the buildings, do not really have semantic labels, right? You are able to understand that there is room 1, maybe to room 16, but you are not able to understand if a room is a kitchen, it is a bedroom, is a bathroom, and so on. And for the buildings, the same. We don't know if a building is an apartment building or is a university, maybe. So the final part of the 3D scene graph construction is really about inferring these missing labels, okay? So in the scene graph, we are missing labels for the rooms and the building. Can we infer those? It turns out that this is, for humans, is kind of an easy exercise. If we know the objects which are inside the room, we can easily guess which type of room we are looking at. So for example, if I tell you that in a room there is a bed, there is a book, there is a chair, most likely you'll be able to say, well, that's probably a bedroom, right? So we would like to do the same kind of inference with our system, with our robots. The old style way to do this would be to do a probabilistic graphical model and try to do inference of the graphical model. That requires hard coding all these factors. It's a little bit tricky. So maybe the new version of this would be to use graph neural networks. How many of you are familiar with graph neural networks? Nobody? OK, few. All right, good. So in graph neural networks, you take a graph, imagine that maybe like 1, 2, 3, 4 are objects, and 5 is the room. So you build a graph, and you learn some neural network, and you're doing message passing on the edges of the graph. So the nodes are exchanging messages, and they're essentially converging on an embedding, on a vector for each node. And then by classifying this embedding, you can classify the node, for example, node 5 as a bedroom versus a kitchen. Okay? So we consider this as a baseline for our experiments, but actually we proposed an architecture which is very simple. It's a basic, simple variation of graph neural networks, but that has much better properties in practice. That is the idea of a neural tree. So it's a new architecture called the neural tree. The idea is very simple. What we say is that you do not have to do message passing on the graph. You actually have to transform the graph into a tree, and then you have to do message passing on the tree. So transforming the graph into a tree is something that is called tree decomposition. It's a standard graph theoretic trick. Essentially, you can see that the tree is encoding at the different nodes subgraphs of the original graph. And then you're reorganizing this tree in a way that you include all the nodes in the original graph, but as a tree structure. Okay? So again, we say you convert the graph into a tree through tree decomposition, and then you do message passing over the tree instead of doing message passing over the original graph. Now, people like Dieter would say, well, that's like probabilistic graphical inference. That's something like that is called junction tree. And indeed, that's exactly what we are doing. We're bringing insights from probabilistic graphical models. We're applying them to graph neural networks. And we are showing that by doing that, we get much better theoretical and practical performance. So let me spend one slide telling you about both the theoretical and the practical performance of this neural tree. It's a long theorem. Let me summarize for you what this is about. So the theorem is saying that let's call G the function that the neural tree can approximate. Right? The neural tree is kind of a function. Right? So G are the functions that the neural tree can approximate, and F are all the probability distributions, are the functions corresponding to probability distributions over a graph. So the theorem is saying that the neural tree can approximate any distribution over the graph with an error epsilon by using a number of parameters, n. You can think about that as the number of weights maybe in the neural tree. And the number of weights will depend linearly on the size of the graph, and will only have a bad dependence, an exponential dependence on the tree width of the graph. Okay? So again, you show the tree width of the graph will show up, meaning that if the tree width is small, this number actually will not be very large. Right? So the only exponential dependence is on the tree width. If the tree width is bounded and small, it means that with a reasonable number of parameters, you can approximate any distribution you want over the graph. So if you don't care too much about the theoretical result, the practical performance is actually pretty interesting as well. So the problem we are testing on are this type of problems in which you have missing labels in the graph, and we have to classify nodes. We use the 3D SIMGRAPH dataset from Stanford with a bunch of graphs being collection of rooms and objects. And what you see in the table are percentage of correctly classified items. Okay? So ideally, you would like to have these to be 100%, meaning that you classify everything correctly. In the table, I'm comparing different types of message passing. So you can think about just different protocols. And comparing the result of doing message passing in the input graph, as is done in standard baselines, against doing message passing on the real neural tree, which is what we propose. And essentially, by doing message passing on the neural tree, just this simple trick, you can realize that you can get a huge performance boost. You can see in many cases it's up to 10% boost, which is pretty substantial. At the same time, since we proved that the tree width is small, the runtime of these algorithms will be pretty comparable, actually. Graph neural networks will be 46 milliseconds in the forward pass. Neural tree will be 65. So, yeah.
Does 65 include the tree decomposition?
I think so, yeah. Yeah, and the tree decomposition is really the key part, because that's the part that will explode if you have large tree width, and instead will be pretty small if you have small tree width. Good question. So let me spend maybe one slide showing what is the integration of Hydra with this idea of neural tree for room classification. And then I will show a slide about applications and things we can do now with the neural tree, with the SIGGRAPH. So again, images, semantic segmentation. And you see here that the robot is starting to explore a kitchen in this case. So you see the trajectory of the robot. The robot is detecting a table, maybe appliances, is detecting a bunch of things in the kitchen. And then the neural tree is doing at the high level inference over rooms. So it's able to understand that that's a kitchen. The robot keeps exploring. It goes up the stairs in the apartment and is finding a bunch of other rooms. And eventually we'll get into a bedroom. Like, there's a bed over here, and we'll be able to classify that as the bedroom. Of course, not perfect. If you stare at this video close enough, you will see that some of the rooms are misclassified in a very predictable way. The rooms that get misclassified are the ones without distinguishable objects. So you can do a great job at classifying kitchen and bedroom, but maybe you do a poor job at classifying hallways or rooms for which there is no clear identifying object for that room. Okay, so again, this is an apartment building. I think there is a top floor and there is a floor downstairs. Hopefully that's feasible. Okay, now that we have these SIGGRAPHs, we explored a number of applications, or a number of potential uses of these SIGGRAPHs. We explored just few things here. There is much more you can do. But if you have a hierarchical representation, the first thing that you can start doing is think about hierarchical planning. And we show that essentially by planning at the level of rooms, buildings, and so on, we can speed up motion planning by a substantial amount. In the table, we're doing something very simple, A star, comparing A star on the voxel-based representation against A star on the SIGGRAPH, comparing larger scenes with one building, 2 buildings, or 6 buildings. And you can realize that you have just a huge speed up by doing hierarchical planning. We've been using this representation for object search as an internal representation for reinforcement learning. And in this case, essentially what we do, we take the SIGGRAPH and we learn a graph neural network to output an action that the robot has to do to search for objects. And we show that this representation is much better, for example, than doing pixel to action object search. And then we also do some application to multi-robot systems in which multiple robots will have to share this representation, and maybe they will compress it as they share to minimize the bandwidth. So for example, here, not sure this is super visible, there is a robot which is building a SIGGRAPH, and it has to communicate a compressed version of the SIGGRAPH to the other robot. You can think that the robot can essentially just send information about the rooms and a little bit of a compressed information rather than sharing the entire SIGGRAPH. Okay, so I will switch gear and move to the second topic. So far I told you about hierarchical representations. In the next part of the talk, I want to tell you about focus on more safety-critical applications and tell you that these applications require certifiable estimation algorithms that are able to distinguish correct estimates from incorrect ones. Okay, so think about a self-driving car. Yeah.
So before we move on, two related questions. First one, have you looked at how to deal with dynamics changes in the environment, which is always when you do these dense mesh kind of representations, of course, kind of tricky with furniture, chairs and stuff like that moving around. And related to that, then I can see how you need maybe the dense representation to build up your graph structure and the data set of where the objects are and things like that. Could you imagine almost getting rid of that for most purposes, and then in the end, assuming that your robot can figure out the details when it gets to a location, and it doesn't have to remember that across time?
Great question. So the dynamic part, partially we thought about it. In particular, when there are humans around, we thought about removing humans from the mesh. We're working right now on a bit of a more general framework to handle dynamics. The truth is that the mesh is making that quite easy, because essentially you can break down the mesh and have things moving independently. So we like the representation for that reason. So I think it's possible to extend to dynamic things. And we're thinking about some unified framework that can essentially reconnect fast changes, as the robot is exploring, with more changes over a long time horizon. But I think that's feasible to do. The second question was about what was the second question?
Yeah, if you can almost get rid of the
Yeah,
metric.
the mesh, the truth is that we try to rationalize the use of each layer of the representation for a task. I think the mesh is pure visualization. You really don't need it for anything. So you can really drop it if you want. And probably if you have to do some sort of local manipulation, you would build a much better local map instead of storing this. Yeah, so think about this as more for visualization. The graph of places is something that I don't get to talk too much in details, but essentially for the graph of places, for each node, we have a sphere of free space that we attach to each node. So the graph of places is kind of an approximation of the free space of the environment. You can do a lot of navigation with that. Great, okay. So certifiable algorithms, think about self-driving cars. The question is, I'm detecting a car, I'm estimating the pose of the car. Can I trust the detection or not? So in this regard, we started thinking about robust estimation as a general framework for perception problems. The truth is that in many of the nice videos I was showing in the first part of the presentation, in the background, we are just solving estimation problems, right? We are solving estimation problems maybe to localize objects from images or from point clouds, or we are solving estimation problems for SLAM, for example, to estimate the trajectory of the robot. The nice thing is that these estimation problems will have a very unified way to write them down mathematically. You can think about optimal estimation as solving an optimization problem in which you want to figure out an estimate of a variable x. For example, you want to localize you want to estimate the pose of a car. Given a bunch of measurements yi, for example, this can be detections of points on the object you want to localize. And you want to solve this optimization problem by minimizing the residual, which is a function quantifying how well the x is fit in the measurements. And of course, in practice, you will have many measurements, like the M will be a large set of measurements. So what is the problem? It's an optimization problem. In practice, what happens is that many of the measurements will be wrong. Many of the measurements will be outliers. This happens all the time in SLAM because you have incorrect edges in the graph. You have incorrect loop closures because your place recognition modulo is not quite perfect. So many of the yi in SLAM will be wrong. Same for object detection. If you have some detection of points on the car, maybe some of these detections will be wrong. So therefore, many of the yi will be just wrong measurements, will be outliers. So now the problem is to solve an estimation problem in the presence of outliers. And again, you can say, look, well, people in the 60s or the 80s, people from robust statistics, they told us how to solve this problem, right? They told us that you just have to put, instead of a quadratic cost, you have to put a robust loss function, right? Robust loss function rho. And the rho is designed with a shape that is minimizing the influence of outliers. Now, the issue is that people in robust statistics didn't tell us how to solve this optimization problem, because it turns out that for common choices of the rho, this optimization problem is intractable to solve. It's very hard to solve, provably hard to solve. People in robotics and vision have worked on this for a long while. People in robotics really like local solvers, in which think about gradient descent. You start from an initial guess, and you try to minimize locally the function. The issue with that is that local search methods are easily stuck in local minima, which corresponds to bad estimates in general. People in vision really like RANSAC. RANSAC is a great algorithm, very established. Unfortunately, RANSAC will not really scale to large problems, will be restricted to small problems. The thing that really bothered us when we started this investigation is that both of these methods will just fail without notice. What does it mean? These methods will give you an estimate for x. This estimate can be completely wrong, but they will not be able to tell you if the estimate is correct or wrong. So this really led us, for us to think about certifiable algorithms. Certifiable algorithm is something very simple. It's an algorithm that is able to compute an estimate, and either is certifying that the estimate is optimal for this optimization problem, or detect failure otherwise. So I'm giving you an estimate. Either I tell you that you can trust it, or I tell you, be careful, don't trust it too much. So in terms of certifiable algorithms, we really produce a toolbox of methods, not a single method, including algorithms based on graph theory to prune outliers, heuristic algorithms for optimization called graduated non-convexity, as well as more formal moment relaxation methods, which are providing certificate of optimality in this case, or are detecting essentially bad solutions. What I want to do in the next few slides is to do a little bit of a deep dive on this part, which is a little bit more mathematical, but I think it's pretty cool. So let's try it out. Before I go into the math, I just want to tell you that figuring out the math for these problems typically pays off in the sense that now with this toolbox of algorithms, we have just much more robust tools for estimation compared to where we started. So for example, now you can do pose estimation in point clouds with algorithms which are robust to 95% random outliers. You can do pose and shape estimation of objects with robustness to 70 to 90% of outliers. And you can definitely do SLAM with much more robustness compared to where we started. All of this is open source, and indeed the SLAM part is also, right now, is released as MATLAB, as part of MATLAB Navigation Toolbox. So that's just like a little bit of a way to say, we care about practical algorithms. If you do the math right, you will get better performance in practice. So I want to try to spend a few slides here in telling you about how to get performance guarantees, how to get this kind of guarantees of optimality in robust estimation problems. And the problem we want to solve is that we have some robust estimation problem. Again, we are given some rho and our function. We want to compute the x. The first insight to solve this problem to optimality is to realize that for typical choices of R, so for typical perception problems and typical loss functions, you can rewrite this optimization problem as a polynomial optimization problem. What is a polynomial optimization problem? It's nothing else than an optimization problem where the cost function and the constraints are just polynomials. You know, x1 squared plus 2x2, just real polynomials. How do we prove this? Well, we take a bunch of different problems in perception, single rotation averaging, multiple rotation averaging, everything that is underlying, for example, structure from motion, SLAM, calibration, object pose estimation. And we can show that with the choice of R in these problems, you can manipulate the problem into a polynomial optimization. Let me give an example. If you take point cloud registration, in point cloud registration, you want to align two sets of points, Pi and Qi, and you want to compute a rotation and translation, which is aligning these two sets of points. Well, if you stare at this problem, you realize that the objective is actually quadratic, so that's a polynomial. And if you stare very closely, you also realize that the constraint that the rotation is a proper rotation matrix in SO3 can be also written as quadratic equality constraints. So that's also a polynomial. Okay? And you can repeat this exercise for all the problems here. You will still get a polynomial. Now, what happens if you add the loss function rho? Well, what we show is that for these 7 choices of loss functions, which are pretty common, maximum consensus is the typical approach in vision, L1, Uber, truncated least squares. For all of these, we still show that you can massage this equation into a polynomial optimization problem. Let me give an example. You get a truncated least squares function, which is quadratic in a region and then flat otherwise. What you can do, you can write this cost function by using a binary variable theta, and theta is deciding between the quadratic region and the constant region. And you realize that if before we had a quadratic function, now with the theta we have a cubic function, still a polynomial. Okay? And by the way, the theta being a variable in 0, 1, that's also like something that you can write as a polynomial constraint. Okay. So hopefully I convinced you that for many perception problems, you can rewrite this as a polynomial optimization problem. Elegant, but not useful yet, because polynomial optimization problems are still hard to solve. You can write down binary optimization, integer optimization as polynomial optimization, so they are very tough problems to solve. So what is the payoff here? The payoff is coming from the second insight, which is for polynomial optimization problems, there is a very systematic way to relax the problem to a convex semi-definite program, so to something that is tractable, is solvable in polynomial time, using a tool that is called the Lasserre hierarchy of convex relaxations, of moment relaxations. So how many of you have heard about Lasserre's hierarchy of moment relaxations? It's always like that. Everywhere I go, like 3 people at most in the room heard about it. I want to tell you, in a slide, what this is. The truth is that this tool is so general, as polynomial optimization is, that even if you don't care about perception, even if you don't care about robotics, chances are you might use this tool for your problems, right? And indeed, these tools are popular in control and in other fields as well. I will try to give you the simplest explanation I can, because I think the idea is quite intuitive indeed. So we want to solve this polynomial optimization problem. Just for the sake of this explanation, let's assume that we have just 2 variables, right? So the vector x is x1 and x2, and all the polynomials are of degree up to 4, Actually, that's what happens for a lot of these problems. For us, the degree that we see is not too high. Okay? So for the example, let's assume degree less than 4. What the moment relaxation will tell you is that you have to do two things. Well, first of all, you have to define a monomial basis. That's just a vector in which you are arranging your unknowns and all the monomials which are functions of your unknown from degree 0 to degree 1 to degree 2. Right? So the x1 and x2 are your variables. You build a larger vector which is containing your variables, the square of your variables of degree from 0 to 2. In this case, the 2 is something that you decide. It's called the order of the relaxation. Let's assume that you have order 2. The second step is that you have to build the moment matrix, which is just this vector multiplied by itself. Okay? So what is that? It's just a larger matrix that is containing all the monomials from degree 0 to degree 4. That's it. It's just a collection of monomials of degree 0 to degree 4. And now the intuition is straightforward. If I have a matrix which contains all the monomial from degree 0 to degree 4, I can write any polynomial of degree up to 4 as a linear combination of the entries of this matrix. Okay? So I can take this matrix, I can do a linear combination of the entries, and I can produce any polynomial I want, which is great. Okay? So, and indeed, I take the P, the H, the objective in my problem, the constraints, I can write them as linear functions of the moment matrix. Okay? So I can transform something that is very tough into something which has linear constraints, a linear objective. What is the catch? Of course, there must be a catch. The catch is that the moment matrix by construction is a vector by itself. That's by construction a positive semi-definite matrix, which is fine. I can enforce that the matrix is positive semi-definite. That's a convex constraint. But the matrix has to be rank 1, okay? Because it's a vector by itself, has to be rank 1. And enforcing the matrix to be rank 1 is a non-convex constraint, okay? So I cannot enforce that. So what Lasserre hierarchy is going to tell you is that you just have to drop. You keep the entire thing, but you drop the rank constraint. And as a result, you get a convex semi-definite program. You get something that is tractable to solve. And the recipe will also tell you about adding extra constraints. For example, if you stare enough at this matrix, you realize that some entries will show up in multiple locations. So you can add constraints that are enforcing that repeated entries of the matrix will be the same. Okay? But so far, what we got is we converted a difficult and very general polynomial optimization problem into a semi-definite program that can be solved in polynomial time. Why is this interesting? We did this approximation of dropping the rank constraint. Why is this interesting? Well, it turns out that there is a beautiful theory behind this kind of relaxation, which is summarized in the theorem over there, and I will summarize just the two main points here. First point is that if you solve this problem, again, that's easy to solve. You get a matrix X, and the matrix has rank 1. The solution has rank 1 for some reason. Then you can map that solution to an optimal solution of the original problem. In other words, if you solve the SDP, this convex problem, you get a rank 1 solution, you're done. You solve the original problem to optimality. And the second property will tell you that if you increase the order of the relaxation, so if you make the X larger and larger, eventually you will get rank 1 solutions. Okay? So it's a general recipe actually to solve. Eventually this will solve the original problem. What is making this interesting for us is that empirically we observed that the relaxation is commonly producing rank 1 solutions for our perception problems, and is doing that at the lowest relaxation order. So it's doing that for small x's. And the relaxation will keep producing rank 1 solutions even if you do some trick to make the relaxation even smaller. If you do some trick to sparsify and to make the x smaller, the relaxation will still be good. So in conclusion, for the first time, we can solve robust estimation problems showing up in perception, some of the robust estimation problems showing up in perception to optimality, or at least we can compute a suboptimality gap for the solution that we have. Just a little bit of empirical evidence for this. 3 problems, we consider many, but just 3 problems. Single rotation averaging, multiple rotation averaging, and point cloud registration. The first column is showing the suboptimality gap. Okay? So if this is 0, it means that we got optimal solutions. And the only thing you have to look at is stride, which is the blue part, which is our solver. So you can see that the suboptimality is less than 10 minus 10 here, 10 minus 10, and probably 10 minus 5 or 6. So it's very close to 0. So we get empirically optimal solutions. And of course, that's not always the case, right? There are cases in which we fail to give the optimal solution. That's expected. It's an NPR problem. We cannot really hope to solve all possible instances in polynomial time. And the plots on the right are just showing that whenever we get optimal solutions, essentially these translate into estimation errors, in this case rotation errors, which are small for increasing number of outliers. And you see that the outliers here are going from 0% to 80, 90%. Okay? So if you're able to solve this problem to optimality, we can get good estimates in practice. Okay, so I have much more to say about this. I will never get to this part, but essentially we have even stronger guarantees about how far are the estimates from these relaxations from the ground truth. I will have to skip that, and I will move to the final part of this presentation, which is going to be shorter, in which I want to connect the idea of certification with the idea of self-supervision. So the point I want to make is that certification and self-supervision are twin challenges, in the sense that if we can certify correctness, we can learn without supervision. What is the context here? Well, imagine that so far we are able to solve some estimation problem in which we are given points on the car. In this case, I want to figure out the pose of the car, right? So we have measurements, that's the yi, and we're estimating the x, which is the pose of the car. The truth is that the measurements are typically provided by a neural network, right? So a neural network is taking the RGB data or image data and is extracting the measurements, is detecting these points for us. So the question is, now that we have better algorithms for estimation, can we use them to kind of self-supervise or improve the neural network detecting the points in the first place? I will show a couple of animations because the idea, I think, is straightforward. It's about self-training. That's the name of the idea. So imagine that I give you a neural network which is trained maybe in simulation. So it's not a great neural network, hasn't seen real data, it's just trained in simulation. And now I want to do, I expose the neural network to a batch of real data. So these are 3 real images, let's assume. And I want to learn from these images without supervision. Okay? So on the real data, I don't provide any supervision. Well, what you can do is that you can do a forward pass of this network, and you can predict the key points. You can run our estimation model, and then you can get an estimate, right? So some of the estimates are incorrect, like these two. Some of the estimates are correct. If you can do certification, so if you can distinguish correct estimates from incorrect ones, what you can do is that for the correct estimates, you can treat them as pseudo-labels, and you can backpropagate them through the neural network, and you can improve the neural network. You can take another batch of data. Maybe now the neural network is slightly better. You repeat the exercise. In this case, the neural network is getting 2 examples right. You can backpropagate and further improve the neural network. And we keep doing this trick. Actually, this trick for us is done at each iteration of stochastic gradient descent. So at each iteration, we take a batch. Instead of just backpropagating all the batch, we are more selective about backpropagating only the certifiable instances. And hopefully, after iterations, of course, we cannot prove that. We do not have proof for that. But iteration after iteration, the expectation is that things will get better. Yeah.
Is there possibly a catch where initially you can only you get correct results or certifiable results on, let's say, a certain class of cases, and you're now gonna kind of start improving your network for that class of cases? And could there be something where, and you hope, of course, right now that it's going to generalize to these other cases that weren't there, right? But it could also be that you're just going to start totally overfitting to that subset of cases, and then you might never get better.
On these, no guarantees. We don't see like a kind of mode collapse in which you overfit the specific cases, but it's totally possible. I cannot guarantee anything. I can tell you empirically the performance you get, and the performance is promising, to be honest, but I do not rule out that there are corner. I think the 2 immediate corner cases, one is what you said. The other corner case is that maybe the network is so poor to start with that you have 0 certifiable instances and there is nothing to backpropagate. So the results are more promising than that, but a lot to be done. I think the idea, by the way, is quite general. So we are exploring this for object pose estimation, but in principle, you can do similar things for maybe SLAM and other problems. So the architecture that you have to imagine for this kind of self-supervised learning, let's assume that you have an input. We have input data, let's assume is RGBD data. So there is an object, like an image, in a point cloud. We pass it through the neural network that we want to self-supervise. We apply some fancy optimization algorithm to optimize the solution. And then we have a certificate that is telling if the output is correct or not. So that's the basic architecture. Actually, in the latest paper, that is the one I'm listing here, we also show that this idea actually generalizes pretty well to putting a bunch of things in parallel, and you can have essentially different branches of this ensemble architecture because there are multiple branches. You can have each branch supervising the others as well. So lots of details. I think the most important thing is probably the plot. This is the type of behavior that we see. So on the x-axis, there are the iterations of stochastic gradient descent. And on the y-axis, you can think about this as the percentage of successfully estimated poses. At the beginning, the network is not very good, right? So the performance is very poor. And indeed, the object, which is this scan in this case, is not well aligned with the green point cloud. As you keep going through these iterations of self-supervision, essentially the performance gets better and better, and eventually, the performance is pretty good. Turns out, I think, is the most surprising thing of this research line is that the result of this self-supervision idea is comparable and sometimes is even better than supervised baselines. So, for example, we have here cozy pose and another baseline. We do comparably well to those, even though we're not taking any supervision. So let me make this a little bit more quantitative, and this, I think, is probably my last slide. The quantitative plot is this ADA score. So you can imagine that here we want the plot to be on as much as we can on the top left. This plot is kind of quantifying the error that you are making, and you want that as many instances as possible have small error. Okay? So we want the plot to be on the top left. And I'm comparing different approaches. The blue one is the proposed, which is not taking supervision or real data. The dashed line is an approach which is cozy pose. Many of you might have seen that. It's a competitive baseline like in the BOP challenge. And there is this other one, which is not super visible, but is self60++, which is a self-supervised baseline. So essentially, we can do much better than this. This plot is averaged over the 16 objects of the YCB dataset, YCB video dataset. And I think here we have some breakdown by objects, but the performance is the same. We get quite good performance in a self-supervised way, and we can compete well against cozy pose, which again is a supervised baseline. Quantitative results are looking good as well. But, I will not insist too much on that. Okay, so promising, a lot to do on this research line, but I think it's nice that there is this connection between certification and self-supervision. So I think this brings me to the last slide I have for the talk. In this presentation, I just made 3 points. The first one was about scalable robot perception requiring metric semantic hierarchical map representations and algorithms to infer them in real time. The second point was about safety critical applications requiring certifiable estimation algorithms that can distinguish correct results from incorrect ones. And the last point was about connecting certification with self-supervision. If we can check whether an estimate is correct or not, we can learn from the correct estimates. So I will finish here by thanking our sponsors enabling this work, and definitely thanking you for your attention.
Thank you. Any question?
Was so clear that
I have a question if nobody else has a question. But for the hierarchical map stuff, it seems like all the levels of hierarchy are like abstractions that we as people would come up with.
Yeah.
Have you also explored like learning those kinds of levels of abstraction?
Yeah, you can do that. And there are people doing this kind of state space abstractions. I think the fact that we are preserving the symbols is somehow a little bit on purpose, because eventually we want to execute essentially natural language instructions based on this. So we don't want to drop, actually, the fact that these are all interpretable symbols. What we are doing right now is we are coming up. So what is bothering me is not that these are interpretable symbols. What is bothering me is that we are hard-coding the layers of the representation. What we are thinking about right now is to come up with an approach which can figure out what are the right layers for a task. So I would like for my robot or for my system, for the robot I'm designing, essentially I give the robot a set of instructions, and the robot has to come up automatically with the right hierarchy that it has to ground in the sensor data. Okay, but I still see a role for like, the symbols. I don't see a reason to drop those. Wait, okay.
Maybe one quick on the, I like the certification and the self-supervision. Is there possibly like a soft version of something like that where you can certify that you're close to the correct answer at least, and you set for kind of like a weighted self-supervision or something like that, where you give lower weight to those that are noisier or something like that?
Well, we are actually thinking about, we see some connection even with robust estimation in a sense, like, in which right now we're doing kind of a binary classification of things. Maybe there is a little bit of a reweighting scheme instead that you can do. So we thought about that. We haven't explored that, but I think it's a good idea. The other thing that I think is a good idea and we haven't done, we don't know how to do that actually, is to learn from incorrect samples. Like not nearly correct, but completely incorrect. Can we learn from those? Like, as humans, we do that all the time, right? So here instead we drop whatever is not certifiable, we don't learn from them. And that's clearly a gap, but I don't know how to do that. Maybe some contrastive learning, but it's not obvious how to do that in this case.
Thank you again.
All right, thanks everyone.